Hey guys, welcome back. This is actually I believe our second to last week of assignments. So just about, I think, four more lessons to go. We're going to talk about acids and bases. I wish we had more time, but so there's going to be some things that are kind of left out. We're going to do our best. We're going to start with what you saw on the CK12 stuff about just what an acid and a base are. And the first thing you have to understand is that water undergoes what's called self-ionization or auto-ionization, sometimes it's called. So if you have two water molecules colliding inside of your water bottle, um, or a pot of water or whatever, what will happen is they will actually have a transfer of one of the hydrogen atoms on that water molecule, on one water molecule to the other. Okay, so that's going to result in H3O plus and OH minus. So you can see that one of these two water molecules um, gained a hydrogen, and only the hydrogen nucleus, only the proton. The electron did not go with it. So it's just the positive nucleus, or you could say the excuse me, you could say the H plus ion got added to a water molecule. And a lot of times, actually, you'll see acids referred to as stuff that increases H plus ion concentration in solution. But what it really is hydronium, this H3O plus, because very quickly that H plus is going to attach itself to a water molecule, and that's going to give us hydronium. That leaves, of course, leaves behind hydroxide, which is OH minus, and that's a polyatomic ion that you're already familiar with. Okay, so that is what's happening in all samples of water, but it's not a one-way reaction. It is very much a reversible reaction. And in fact, it's rare when this reaction, I shouldn't say it's rare when it happens, it's happening millions and millions of times a second in any small sample of water. Um, but the thing is that most of the hydroniums and hydroxides then will, or many of them I should say, will collide and give the hydrogen back to the hydroxide to make the two water molecules again. So it's a reversible reaction. And once we are at equilibrium, there is a lot more water than there is hydronium and hydroxide. There are actually really, really, really tiny amounts of hydronium and hydroxide in a sample of pure water. But it's useful to talk about this reaction because this is what makes acids and bases tick. Because um, the very first formal sort of molecular definition of what an acid was made up by this chemist named Svante Arrhenius, and he said that anything that increases hydronium concentration in a solution is an acid. So if I put a substance, um, and prior to Arrhenius, they were able to identify acids based on their properties, which we'll talk about in a second. But he realized that HCl, hydrochloric acid, is an acid. So, but if I react it with water, this is the thing that makes it an acid. The HCl reacts with the water, and the H from the HCl is transferred to the water, and the result of that is hydronium. And then what it would leave behind would just be the Cl minus. So this is called an ionization equation because we're creating ions. And this is why HCl, to Arrhenius, he said, well, on the molecular level, what is an acid? It's not just something that tastes a certain way or conducts electricity or whatever. Specifically, it is something that creates more hydronium. Because as we've already discussed, there's a certain amount of hydronium in pure water already. But there's the same amount of hydroxide. But by producing more hydronium here, we can identify HCl as an acid because that's what it's done. Now, another ionization equation you could try is going to be HNO3. So that's called nitric acid. We'll get to naming in just a minute, but go ahead and see if you can identify, based on your example here of an ionization equation, what the HNO3 ionization equation will look like. Okay, so there you go. We're forming again hydronium. The only difference between these two is we're forming nitrate as the negative ion because that was the negative ion in the HNO3. Okay, and then bases, according to Arrhenius, were anything that increase this other polyatomic ion, hydroxide. So anything that increases hydroxide is a base. Now, an Arrhenius base is very simply something that contains hydroxide. And all it does is it dissolves. So, for example, if I had barium hydroxide, remember that barium is +2, so there's two hydroxides. It dissolves in water. And so whenever that happens, we just put water over the arrow because we're not actually changing the water molecule this time. We're simply dissolving the barium and the hydroxides. So that's going to result in one barium with a 2 plus charge and two OH minuses. Okay, so that's what makes barium hydroxide a base, according to Arrhenius. It increases the concentration of this guy over here, hydroxide. So that's what an ionization for a base looks like. Try this one. Okay, there you go. So it's just dissolving in water. It's not changing the water, and it's splitting up and forming K plus and OH minus. This time, of course, only one OH minus because there was only one in the potassium hydroxide in the first place. All right, acid properties. Some things, this is how they would have identified acids many years ago before pH probes and pH indicators and all that stuff. Literally, you would have tasted a small amount of it. So very dangerous. But acids taste sour. So think about sour candies. Think about grapefruit. Most citrus fruits have fruits in general actually have small amounts of weak acids in them that make them taste sour. That doesn't mean that they're unhealthy. A lot of these acids are beneficial, like ascorbic acid is vitamin C. Um, Citric acid is useful in your body in a lot of ways. So there you go. Your body is able to your tongue is able to identify an acid. Um, and if it's too strong, if it's too sour, of course you're going to spit it out. If you think about your taste buds being an evolutionary adaptation, that makes sense. If you're foraging for food and you're not going to the supermarket or the restaurant, you're just out in the woods picking berries or whatever. If something is super sour, that's probably going to tell you that it's a little bit too dangerous to eat. And so that's why that property is there. It's not so much an acid property as it is a human property, or I should say an animal property. We have taste buds, so help us out sometimes. They conduct electricity. So acids conduct electricity because they have ions. Anything that has ions, like for example up here with the hydronium and the nitrates, can conduct electricity. Reacts with active metals to produce hydrogen. By active metals, if you go back to our activity series from first semester, if you were to take some HCl and react it with, let's say, magnesium, that magnesium is pretty high on the activity series. So that magnesium is going to replace the hydrogen and give you MgCl2, and it's going to liberate, set free, some hydrogen gas. So when you put acid on a metal, you'll see some bubbling, and that bubbling, of course, is going to be your hydrogen. Equation's not balanced. There we go. All right, and the last one is it neutralizes a base. So acids neutralize bases. We'll talk about neutralization a little bit more, I think, next time or next week. All right, how would you identify a base? Well, bases tend to be even more poisonous than acids. They tend to be associated with like plant toxins, things that insects, that insecticides, things that make you sick if you eat it. Um, and that bitter taste has evolved to tell us to stay away from some of those substances. Some of them are milder and actually make you feel good. Caffeine is a plant, is a basic plant insecticide, basically a pesticide, meant to keep insects from eating the coffee beans or chocolates. It's the same thing, and the cocoa bean. Um, but or nicotine in tobacco plants, all the different drugs that are in a poppy plant, from morphine to, they're all in there. Those are plant pesticides, and we taste them as bitter because if you eat too much of it, then it can actually poison you. Caffeine, of course, would take whopping amounts, especially straight from the plant, but morphine, not so much. So anyway, they taste bitter. Soap, if you've ever had your mouth washed out for using bad language when you were a kid, um, that tastes extremely bitter. It's disgusting. That's why it's a punishment, because soap is basic. And if we bump down 2 spots here, soap feels slippery. Also tells you that soap is a bit basic. Um, Bases conduct electricity because they have ions too, just like acids, like K plus and OH minus. And then finally, they neutralize acids. If you've ever taken a Tums, like an antacid, that's what you're doing. You're neutralizing the excess acid in your stomach with a little bit of base. And we'll talk about that later on, like I said. Okay, last thing we want to talk about is how do we name acids? So I've thrown a couple acids at you, and we haven't really talked about their names. So the first example I gave you was HCl. Here's how this system works. When we're naming the acid, all you have to do, and by the way, we're not going to worry about bases because bases, you don't change their name at all. It's just like enzyme hydroxide, potassium hydroxide, barium hydroxide, sodium hydroxide. There's no new naming system. But acids, there actually is a separate naming system for acids. Okay, so we could call this hydrogen chloride, right? And because it has that ending of "ide," when we name it as an acid, we're going to change it so that it has a prefix hydro and a suffix ic, and then of course the word acid goes after it. So if it ends in "ide," like hydrogen chloride, okay, then it's going to become hydrochloric acid. Okay, so another example, let's say we went with H2S. So that would just be hydrogen. I know that looks like a 5, but that's an S. That's just hydrogen sulfide, meaning sulfur from the periodic table with a -2 charge. So we call it ide, right? So if this is hydrogen sulfide, what does its name become? Okay, there you go, hydrosulfuric acid. Don't worry too much about where exactly you put the ending on that. If you said hydrosulfic or something like that, there's some picky little rules about where to put the ic ending. As long as you're replacing the ide with ic in some way, that's good enough. All right, the next type would be 8. If you have a polyatomic ion that ends in 8 paired with hydrogen, like for example, H2SO4, hopefully at this point you recognize SO4 is sulfate, right? So therefore, this could be called hydrogen sulfate. So if it ends in 8, no prefix anymore, but we do still give it an ic suffix. So this would be called sulfuric acid. And this is probably a familiar name to you. This is what's in like battery acid. All right, let's try another one. Let's give us another 8 ending. Let's go with, we did this one earlier, but I didn't say what the name was, or maybe I did, but anyway, try that one. Okay, and so this one is not nitrate, hydrogen nitrate, but nitric acid. Okay. All right, then the last rule, if the polyatomic ion ends in "ite," then you are going to have an "us" ending. So let's go ahead and say, let's say we had some hydrogen sulfite, SO3, 2 minus is sulfite. Okay, so that's going to be not sulfuric acid because this isn't sulfate, this is sulfite. This is going to be sulfurous acid. Okay, all right, so let's try another one. Let's go with hydrogen phosphite. What do you think about that one? All right, this one is, instead of phosphite, this is going to be phosphorus acid. And again, there's kind of an extra syllable in there. It's tricky. Don't worry too much about it. If you were to call this phosphorus acid and not put the OR syllable in there, not a big deal, as long as you understand what the system is. All right, guys, have a good day, and see me with questions in our Zoom session if you have them. We'll see you next time.